Good morning. It's my pleasure to introduce to you our first speaker of today, Professor Bar-Natan from the University of Toronto. He will be sharing with us about shifted partial quadratics and Pushwards and signature invariants for Tangles. Let's welcome our speaker. I've got handouts here if you would like them.
So yeah, I'll start with a long list of meta preliminaries. So my talk will follow a handout, and I hope you all have a copy. Thank you for inviting me to Icerm. It's a wonderful place. If you are a Zoomer, please, please, webcam on. I want to see your face. Also, my talk has a URL. It's written here, and you can find the handout and links to the program and everything over there. Everything that I will be talking about is joined with Jessica Liu, who is seated over there, and she is absolutely wonderful, and I hope you'll hear a lot more from her in the future. There is some prior art on the subject. So basically the subject is signature invariants of Tangles, and there is prior art. And so here are the links or the references. And I think what we do is more general and more direct, more straightforward. But you can check and see for yourself. I have to acknowledge two grants, the INSERC and the Arthur Chu, the Chu Family Foundation. And finally, I can more or less start. So thank you, Zoom people, for joining. Basically, my whole career, or half of my career, I've been computing zombians of unfinished columbaria. So let me explain. So first of all, a zombian is something like, is something that people like me would like to compute. And it's supposed to rhyme with Lagrangian, Hessian, Wronskian, some complicated thing that you want to compute. A columbaria, you can look it up in the dictionary, a columbarium is a structure that has many cavities in which you put urns with ashes of the dead. An unfinished columbarium is one in which maybe the structure is made, but not all of the urns are already allocated. Not all of the cavities are already allocated. And the question is, what can you do now? What can the zombies like me do now when the columbarium is still unfinished, so that when new information will come in, you will be able to complete the computation, you will be ready and be able to compute the computation more quickly. So, of course, the zombian for me is some sort of not invariant. Kovanov homology, the Jones polynomial, the Alexander polynomial, something like that. A complete columbarium is a knot. An unfinished columbarium is half a knot. So a tangle. Okay? Why do I care? Why do I care about tangles? So first of all, often they lead to faster computations. So for example, think of the Kaufman bracket. You have a knot with n crossing. If you want to compute the Kaufman bracket, you need each crossing to resolve either to a zero smoothing or to a one smoothing. There are two choices, so there are 2 to the n choices overall. So the computation, the time it will take you to compute is roughly 2 to the n, if you are naive. But if you break the knot into 2 pieces, each of which is a tangle with n over 2 crossings, then first of all, you can note that you can break it in such a way that the cut is of length square root of n. So there are roughly square root of n lines going across between the two tangles. That's something that you have to think about, but it can be done. And then the computation time turns out to be 2 to the n over 2 for the first half, 2 to the n over 2 for the second half, and then there is some gluing cost to glue the two computations, and it's roughly 2 to the square root of n, and the point is that this is a lot less than 2 to the n. It's called divide and conquer, and you gain a lot by doing it. Second reason to think about tangles is that you get conceptually clearer proofs of invariance. So, for example, or also proofs of skein relations. So, for example, you want to prove the Reidemeister 3, invariance under Reidemeister 3. Invariance under Reidemeister 3 is just an equality. Two tangles have the same value. Once you've extended your invariant, your Zombian, to unfinished columbaria, then you compute the invariant, the Zombian of the left-hand side, the Zombian of the right-hand side. If they agree, you've proven invariance. Likewise for skein relation. And I think the main point is that it's often fun and consequential. So for the Jones polynomial, if you want to generalize it to tangles, you get temporally leaf algebra. So you learn something, you gain something. For Chovanov homology, maybe this is my big pride, you get unfinished complexes. So, in Chovanov homology, the vector spaces are determined by the cycles in the smoothing. And if you have a tangle, many cycles are not yet completed, so you don't even know what the vector spaces are. So how do you compute homology? And it turns out the answer is that you play some games with category theory, and well, at least it's interesting. It also leads to immense speed up. For the Kontsievich integral, you're led to be thinking about associators. For Higard-Floor homology, you're led to, oh my God. Okay? And really I should say that, I introduced it as divide and conquer, but usually things like that are done more like using knot tees. So you have a knot and a curtain is hiding it, and you raise the curtain slowly, and then you see more and more of the knot, and you try to compute more and more as you raise the curtain more and more. Okay? And this turns out to be more efficient than computing the whole thing at once. So, just still completely vaguely, completely in the abstract, what are a few things that you would want from a computation for the Zombian of an unfinished columbaria? So it must be no smaller, so the computation of an unfinished columbaria must be not much slower than the computation for a finished one, otherwise what's the point? The next thing is that future zombies who are given the output of the current zombies should be able to complete the computation. The next condition is that future zombies should not even need to know the size of the tasks that the current zombies are facing. So basically, I have 1,000 crossing knot, I cut it halfway, 500 crossings are on the left, but the boundary is roughly of size square root of 1,000, so 30. So the future zombies should see information proportional to 30, not to 500. Okay, somehow the current zombies who are doing the current computation should be able to compress the computation only to basically what's on the boundary here. Okay? And finally, we must be able to extend the computation to Z-packs. So Z-packs are zombie processed unfinished columbaria. So you see, when you do this knot tease process or columbarium tease process, when you've reached a certain height, you've computed something. What you see is no longer as an unfinished columbarium. What you see is the result of the computation so far. So you should be able to add a bit of information and move to the result of the computation in the next stage. So your input is not really unfinished columbaria, but zombie processed unfinished columbaria. You need to be able to extend to that. Okay? So having said all of these generalities, here is an example. I challenge you. So I give you a 1,000 by 1,000 matrix, but I'm telling you that 50 of the entries are still unknown. So you have this big matrix, and it's square, as you can see. Sorry, and a few entries are still unknown. What can you do now so that when the new entries come in, you'd be able to complete the computation of the determinant? Sorry, I forgot to say, the determinant is the Zombian is the determinant. So what can you do now so that you can complete the computation of the determinant later very quickly? So I'm really bouncing into you, so I'm really asking you. So let's start. Suppose there was just one entry missing. What would you do? Suppose I gave you a matrix, but I told you that one entry is still unknown. What would you do?
I would compute the cofactor expansion and wait for that term.
Excellent. So you'll be, essentially, you'll be saying, let's put here x. See my hand? Let's put here x. Compute the result as a function of x. There will be a constant term, which is just the overall determinant, and x multiplying a cofactor. And then when x comes, you'll just evaluate this linear function. Good. Now suppose instead of 1, you have 50. What would you do? 50 unknown things. What would you do? Yeah?
One could try to arrange them in the same column or in the same row.
But they're not.
But the determinant is...
No, but they're in completely different rows and columns. You cannot make them be in the same row and the same column.
But sometimes we can switch them, and if we cannot, we just use the Laplace way of computing the determinant once again.
Yes, so you may have answered my question. I'm not sure, because I don't know the Laplace way of computing the determinant. But let me tell you what you don't do. The naive thing will not work, right? So basically, repeating what Ellison, right? Yeah. What Ellison just told us would not work, right? I could just say, let's compute a polynomial in x1 up to x50. The problem is that you'll get a degree 50 polynomial in 50 variables. The space of such polynomial is enormous. Or said differently, the number of cofactors, of minors in a matrix is exponential. So it breaks the rule of do no harm, of do no worse than the basic computation of determinants. Basic computation of determinants can be done using row and column reduction, and it takes roughly time n3. Is this the Laplace way?
No, he meant cofactor.
I don't know. Anyway, so here is what you do.
The question, do you want to know if it's non-zero or what?
No. I want to compute the determinant, right? But I want to do preparatory work now so that I can compute the determinant later. So here is what you do. Well, actually, instead of 50, so okay, those 50s by row and column or by swapping rows and columns can be brought to the lower right corner of the matrix. And I'm doing it only for convenience. You don't really need to do it. And So now I'm thinking I have a matrix which is roughly 1,000 by 1,000, but the lower right corner is unknown, and it's 50 by 50. So basically it's a block matrix, but the blocks are not of the same size. A is huge, 950 by 950, and U, the unknown, is just 50 by 50. Okay? Then I just start doing Gaussian elimination. So I do row operations to turn A to the identity. And as I turn A to the identity, that's like multiplying on the left by A inverse. So B gets replaced by A inverse times B. But that's row operations would do it automatically. Okay? But you see, when you compute determinants using row operations, you have to keep track of what you've, when you multiply a row by 7, you have to divide the result by 7, okay? So here I multiplied by A inverse, so I have to multiply the result at the end by the determinant of A. Then I do row operations to kill C. So once I have the identity up here, I can do row operations to kill C. And when I do it, the resulting matrix will become identity A inverse B, U minus C A inverse B. And the cost here, the change to the determinant is nothing because this is only adding the rows to other rows. This doesn't change the determinant. So the conclusion, but this is a block diagonal matrix. So its determinant is the determinant of the identity, which is 1, times the determinant of U minus C A inverse B. And the conclusion is that, well, the determinant of A, B, C, U is the determinant of A times this formula here. And that does exactly what I want, because, so the information I need to pass on to future generations of zombies is the determinant of A, which is a single number, right? So A was 950 by 950, but I just need to pass on its determinant. And I need to pass on C times A inverse times B, and that's a 50 by 50 matrix. So that's the size that the future zombies are willing to process. And then the future zombies, when they get the information in U, when they learn what U is, will simply add to it, subtract from it, the information that I've passed to them, then compute the determinant, and then multiply by the determinant of A, and they're done. Okay? By the way, completely as an aside, very rarely in mathematics you need to know the determinant of a sum of matrices, and this is one place where you need to do it. Anyway, so I have some questions. I mean, what if A inverse does not exist? What would you do? So you still have homework, I'm afraid. Okay? Also, so, I kind of ignored the issue of zombie processed and finished columbaria. So what would they be in this case? And the real homework is, so the Alexander polynomial is a determinant. So can you use what we just learned to find an Alexander polynomial of tangles? And the answer is yes. But also the surprising answer, the surprising thing is that people do all sorts of much more complicated things to get the Alexander polynomial of it, to get an Alexander polynomial of a tangle. Anyway, can I move on? Is this okay so far?
Sure.
Yeah.
I have just a quick question. So you put the U, the unknown part, in the bottom corner. How do you know you can make it a square? Like, couldn't I have like a whole column with 50 entries?
Oh, I said 50 unknown things. I can always fit them in a 50 by 50 square.
Oh, 50, yes, okay, thank you.
So in fact, I've done a lot more, right? I mean,
Yeah.
I told you how to compute the determinant when 2,500 things are unknown. Okay, but in particular, it does 50 no matter where the 50 are. Okay? Okay, so now let's move on to signatures. So what is the signature of a knot? So let me start with a reminder, though the truth is that it's probably not a reminder because I'm going to describe two formulas for the signature of the knot, and neither one of them is very well known. Okay? But, okay. So basically, I'll tell you about two functions that start from knots and give you matrices. But these are Hermitian matrices, matrices with the property that the matrix is equal to its own conjugate transpose. So it's the same as a quadratic form, whatever that is. And then whenever you have a quadratic form, it has a signature. The signature of a quadratic form is, one way of saying it is to say that you compute all of its eigenvalues, the eigenvalues of the matrix, and you let sigma plus be the number of positive eigenvalues, sigma minus be the number of negative eigenvalues, and then the signature is the sigma plus minus sigma minus. Another way of saying it is that you take this matrix and you are allowed to do row and column operations to it, but in tandem. So whatever you do to the rows, you also do to the columns. So you have like a machine that does row and column operations, but it has its gears interlocked. So whatever it does to the rows, it also does to the columns. Actually, conjugate. I mean, but anyway, then you can show that you can, using these row and column operations, you can bring every matrix to a form where you have only ones, minus ones, and zeros on the diagonal. And if the number of ones is sigma plus and the number of minus ones is sigma minus, then the signature is sigma plus minus sigma minus. Okay?
What's the plus S?
And then for one of these two methodologies, there is also a shift, and then you just add the shift. Okay, you'll see the shift in a moment. Okay? So all I have to do is to tell you how to get from nodes to matrices in two different ways. So first thing you do is you number the faces of a node diagram. So 1, 2, 3, 4, 5, 6. I guess this is an 8 crossing node, so it's going to have 8 plus 2 faces. So I'm going to make a 10 by 10 matrix. And then if you see a positive crossing, so a positive crossing is going to be surrounded by 4 faces. Let's say there are I, J, K, and L, and please ignore the minus signs. The minus signs play some technical role. Ignore them, they're irrelevant right now. So a crossing, a positive crossing, is surrounded by I, J, K, L. And likewise, a negative crossing, which I will denote by X bar, will be surrounded by equally well I, J, K, and L. And I think my convention is that I is the index, that the face that comes in between the two incoming strands. Okay? So, given such a crossing, so you start from an empty 10 by 10 matrix, and given such a crossing, you add to it, so for each such crossing, you add to it in rows I, J, K, L, in rows I, J, K, L, and columns I, J, K, L, the matrix given here. Okay? And you do it for all the crossings, and this fills in much of that 10 by 10 matrix. Okay? Where the entries here, I should have said in the beginning, you have to start with a complex number omega of modulus 1. And then I just, for convenience, I make a few definitions. T is 1 minus omega, R is T plus T conjugate, V is the real part of omega, and U is the real part of the square root of omega. So basically, these are only for convenience to make these matrices appear a little bit simpler. Okay? So So for the so-called Tristram-Levin signature, for the positive crossing, you add this matrix. For the negative crossing, you add that matrix. And then there is a second signature function called the Kashayev signature. And for the Kashayev signature, the matrices are slightly different from these, but they're still Hermitian matrices. Yeah.
When you say add that matrix, do we start with the zero matrix?
So I start with the zero matrix, and for each crossing, I add this 4x4 matrix in the rows and the columns specified. Okay?
What was there?
Yeah, to whatever was there before. So, right.
And you get to pick omega later.
And omega, I think at the end or at the beginning, it doesn't matter. And I should say that for the Kashayev signatures, there is also shifts. So for the positive crossing, you subtract one from the shift. For the negative crossing, you add one to the shift, and then you add that shift at the end. Okay? And by the way, it's an open problem. These two signatures appear to be this, well, as computed on all nodes with up to 14 crossings, I don't remember how far I've gone, they appear to be the same, but, sorry, with a factor of 2, but it's an open problem. Why? And I think it's completely pathetic that a problem about 4x4 matrices would still be open, but it's open. Okay. So now I want to tell you about how to compute signatures of unfinished matrices. And there is a lovely theorem about it. And I'll start with the proof of the theorem, and only then state the theorem. So the proof is as follows. Okay? Suppose you have a big quadratic form. So think Q is the big quadratic form. And it's maybe 1,000 by 1,000, and I divide it into blocks, and A is 950 by 950, B is 950 by 50, B conjugate transpose, well, it's just the conjugate transpose of B because we have some symmetry property for quadratics. And U is a 50 by 50 part, which is still unknown. Okay? And in fact, later, I will call the big space, so a 1,000-dimensional space, I will call it V, and the small space, W, and there will be a projection map phi, which maps the big space to the small space, and it just kills all the vectors, the 950 vectors that are in W. Anyway, so given a matrix like this, how do I quickly make preparation so that I can compute its signature when U will finally be given to me? Answer, I do exactly the same as in the case of the determinant, except it's not quite exactly the same. So first of all, I do row and column operations to A, but now it has to be row and column operations in tandem. So I do row and column operations to A, so as to bring it to the canonical form, which is a diagonal with plus and minus 1s, and the rest is 0. Okay? So A becomes this, and as I do that, since I'm doing row and column operations to A, the part in U remains untouched, but B gets messed up. So I still have, so I have a picture like this, and here I have a messed up B. Whatever the messed up B is, I can kill the part above the dashed line. So I can kill the part which lies parallel to the plus and minus 1s. I cannot kill the part next to the zeros, but I can kill this part basically by doing column operations. So I do column operations with these 1 minus 1s to kill the part of B that stayed here. Okay? As I do that, I end up taking things from here and moving them to here, so U gets messed up. So some matrix F gets added to U. And then I'm stuck. There's nothing more I can do. So what I pass to the future zombies is, well, the signature up here. Oh, I should have said the result now is a direct sum, right? So basically there is this block here and there is this block here. So all I need to do is to pass to the future generation the signature of the big part and the information over here. So what I pass to future generations is the sigma of the quadratic reduced to the kernel of the projection map to W. Right, this is exactly this. And I need to pass on this C and F. But if you look at it, C and F are not fully determined, are not unique. So C is determined up to row and column operations. So row operations on C, which means the same column operations to C applied to C conjugate transpose, and I indicated with this bevel gear here, which, you know, whatever you crunch to C, you have to crunch the same way down here. And F is determined only up to, you can take a row and a column, or sorry, a row from C, multiplied by something and add it to F somewhere. So C is determined, but you have to do it simultaneously for the rows and for the columns. So F is determined up to, you know, taking stuff from C and moving it to F, but doing it in tandem. So with this, in tandem on the columns. Yes?
Is that quadratic going to be F or going to be U plus F, where F is equal to F?
Oh, so what I pass on to the future generation is F.
Oh.
Future generations are going to say, now I learned what U is, I add U and compute the signature of the remaining thing. Okay? Now, if you look at this thing, then F looks like just a quadratic form. It's a Hermitian matrix. But it's not uniquely determined. So in fact, C determines a subspace of W, namely the kernel of C. So think about row vectors, columns that that C maps to 0. Okay? And the fact that I can add rows from C to F means that the quadratic form F is determined only on the subspace which is perpendicular to the rows of C, meaning the kernel of C. So I get a quadratic form, which I will call the push forward via the projection to W of Q. And this quadratic form is defined only on a subspace of W, not on the whole W. And the subspace is the kernel of C. Okay, so I mean, maybe you didn't quite follow. It doesn't really matter. The point is that it's clear that this is something that you could follow if you concentrated. It's just row and column operations. And now let's abstract this. So let's turn it into something completely abstract. So, oh, sorry, here's the abstract definition of a quadratic form. I don't want it right now. So a partial quadratic, so we find that the things we care more about are partial quadratics. So a partial quadratic on a vector space is a quadratic defined only on a subspace of the vector space. That's all. You can add partial quadratics by just you intersect the domain space. If you have a map from V to W and you have a partial quadratic on W, you can pull it back to V. Pulling back is always easy. A quadratic is just a function on a space. So you can compose it with the map psi, and you get, so if you have a function on W, you get a function on V. If the domain space is partial, you just pull back the domain space. So there is a clear notion of the pullback of a quadratic form, and what I have just told you is that there is also a notion of a push forward of a quadratic form. So if you have a map phi from V to W, In our case, it was a projection, but I can make it more general. So if you have a map phi from V to W and a partial quadratic Q on V, then there is a push forward, which is again a partial quadratic on W, and it has the property, and in fact this property defines it, so there is a unique push forward, with the property that for every partial quadratic U, this is the unknown bit, the signature of Q, the quadratic on the big space, to which you add the pullback from the small space to the big space of the unknown part. So basically this was the, so this is our Q. Q is the pullback of U from the small space to a big space, and then I add it to some given Q. So, So the signature of Q plus the pullback of U is some signature on the kernel of Q plus a signature on W of the unknown part plus the push forward of Q. Okay? So this is just the abstract version of this row reduction nonsense that I was showing you before. Now, if you really must, I can make it completely abstract. So the domain of the push forward is the push forward via phi of the annihilator of something, and the push forward itself is defined by pulling back vectors subject to some constraint. I don't know how that works. I can do it. If you want a proof, here is the proof. Okay? The full proof. And thank you, Jessica, for writing it. But I claim that this is exactly what we want. Okay? So, suppose you have a tangle. I made it a weave just to make it simple. Okay? So let me define two notions. So one notion is a face. A face is what you think is a face, but I also include the faces on the boundary. But the faces on the boundary actually is something slightly different. The space between two legs of the tangle, I will call a gap. Okay? It's nearly the same as a face, but not quite, because, for example, when you're looking at a Reidemeister 2, the right-hand side of a Reidemeister 2 move, oh, come on. When you look at the right-hand side of the Reidemeister 2 move, so this is a face, this is a face, this is a face, this is a gap between two legs, this is a gap, this is a gap, and this is a gap. So the same face actually corresponds to two different gaps. Okay? Anyway, if I have a tangle like this, I get a vector space W from all the faces, another vector space, V from everything, another face W from the gaps, and I get a quadratic form, and the quadratic form is defined by summing over crossings of something, so it's fully defined on the parts that have kind of V, like the inner parts alone, and also the interaction between faces and gaps is fully defined. However, it is still unknown what will happen, what the entries that corresponds to two W's, two gaps will be, because that may depend on what we connect on the outside. So, so if I have a tangle, I get a similar structure to the structure I was talking about before. And its invariant will be, well, the pair, the signature of Q restricted to the kernel, so basically the inside signature, comma, the push forward of Q to the edges, to W. And so my ZPACs, my zombie processed unfinished columbaria, what I get after I compute the invariant of half a columbarium, so of a tangle, what I get is a pair, an integer, comma, a partial quadratic. Okay? And now I can make it even a bit cleaner by defining a shifted partial quadratic. So a shifted partial quadratic is simply such a pair. It's a ZPAC. It's the result of the computation. So it's a shift, which is an integer, and a partial quadratic on the vector space. Addition, when you add shifted partial quadratics, you also add the shifts. When you pull back, you keep the shift. Push forwards, you add the signature of on the kernel to the shift, and you push forward the partial quadratic. And the signature of a shifted partial quadratic is defined to be the signature of the quadratic part to which you add the shift. And then you get a reformulation of theorem 1, and it just given a partial quadratic on V and a partial quadratic on Q, the signature of S plus the pullback of U is equal to the signature of W of U plus the push forward on S, and that's exactly the same theorem as before. And another theorem, which I will state only for fun, though it does get used later, is that all of these things are kind of nice. So pullback is clearly functorial, like the pullback of a pullback is the pullback via the composition, but the same is true for push forwards. And also there is some commutativity property under some conditions. I will not get into it. Okay? And now, and here's the proof, but now I can more or less complete the story. So the target space is for a tangle. So if you have a tangle, I will label its gaps G1, G2, G3, G4. So the target space is of my signature for tangles will be shifted partial quadratics S defined on the linear space defined by the gaps. And then there is a theorem which says, which tells you how to compose tangles. So if you have a connection diagram is basically a diagram like this D here, but ignore all the G's and F's. So basically the green lines and the red and the black lines. So if you have a connection diagram like that, it tells you how to compose tangles. If you have 3 tangles, 1, 2, and 3, you plug 1 into 1, 2 into 2, 3 into 3. I'm assuming that these tangles all have 4 legs in this picture. And then the output will be a tangle with 1, 2, 3, 4, 5, 6 legs. Okay? So a connection, a diagram like this is a way to compose tangles. And now I have to tell you how to compose their ZPACs. So their shifted partial quadratics. So suppose I have 3 shifted partial quadratics. 1 for tangle number 1, 1 for 2, 1 for 3. How do I compose them? So there are 2 maps that this picture defines. 2 maps from the space of faces to the space of gaps. One map, psi, maps every face to the internal gaps adjacent to it, to the sum of the internal gaps adjacent to it. So F2 will be mapped to G14 plus G24 plus G33 plus G31. And and the second map, phi, will map each face to the sum of the external faces adjacent to it. So F2 will be mapped to G2 plus G6. However, face number 5 over here is mapped via phi to 0 because there are no external faces adjacent to it. And then the claim is that the composition is, well, you take the direct sum of the partial quadratics on 1, 2, and 3, you pull it back to the faces using phi, using psi, and then you push it forward to the external faces using phi. Okay? So the theorem is that this makes a structure of a planar algebra. And furthermore, if you also define the basic tangles, the overcrossing and the undercrossing, using the formulas I gave before, then this extends to a planar algebra morphism, or to two planar algebra morphisms from tangles to this planar algebra. So shifted partial quadratics. I understand I have to finish. I wish I could tell you more, but everything is implemented. I'm not proud of the implementation because it doesn't look exactly like the math. But it still works, and it verifies Reidemeister 3, it verifies Reidemeister 2. You can compute knots with it, you can compute tangles with it. Here are the Konrad Kinoshita Terasaka tangles. And you know, sometimes you get non-trivial examples. I wish I had even the time to explain how to read the results. But like for the braid B1 shown here, this braid here, the quadratic form is given here. This is for the Tristram-Levin. And the subspace, so basically you should read it, this is F, and up here is C. So you actually get non-trivial partial quadratics and not just full quadratics. And I think I'm definitely out of time, so I definitely cannot tell you how the program works. And maybe I'll say this is the core. Everything else is pretty printing and formatting and nice, like little utilities, but the core is just that, not so much, not so bad. And there are lots and lots and lots and lots of open questions to ask. Not so lots, only 19. And I'll stop here.
Thank you. Do we have any questions? And I was told if you had not asked your questions already, I would kindly take away the option not to use your teaching voice today.
Echoing, I say this is fantastic. I'm sorry I came in late. So I guess a ZPUC, when I pronounce it, it's an envelope for the thing you're actually looking at today, but it could be an envelope for any other construction you want us to think about. So that was the first question.
Yeah,
I got it now.
So of course the quest to compute something that's partially given is not restricted to
Exactly.
right? And of course I don't expect ZPUC to become the official name.
But it
There might
rhymes.
be an official name already.
But it sounds really good because it sounds like what it becomes.
Yeah.
So let me ask you an elementary question, which shows that I only understand things weren't evaluated. So I said during the talk, omega you get to pick. Are there particular values of omega, like primitive eighth roots of unity, that just give interesting information when you actually use?
Yeah. Omega. So the Tristram-Levin and also the Kachayev signatures, both of them are actually functions on the unit circle, and you know, you can plot the values of these functions and you get graphs. So I mean, this is the unit circle opened up in some way. But you get so each is a graph, and the jumping points are algebraic numbers, and the program also gives you what they are, but.
Questions?
Not really a question, but a remark, which is like a funny coincidence. I could not follow everything, but the first part pretty much looked like
So the first part, what?
Where you said we want to compute the determinant, or actually also the signature, is basically about factorizing matrices, like AU factorization. The second part basically LDL factorization. And when you process sparse matrices, there's a certain type of methods, that's the multi-frontal methods, where you also try to do these lotwise updates. And like a funny coincidence, the matrix that you call F, forward matrix, that's the frontal matrix in that respect. So
Frontal.
the frontal matrix.
Yeah.
Actually, not only the F, but also the C, like this angle that you push forward. It's just like a remark that I like to make. And I thought that most of the matrices that you process are quite sparse.
They are, of course.
And then, well, what you do then first is a pass of nested dissection on the graph that's defined by the matrix. That gives you a nice reordering from the matrix. So that could be even improve the efficiency of these things. It's just a remark. Thank you.
Okay, thank you.
Other questions?
I just wanted to ask if that could be extended to notoids or linkoids. Does it matter where the ends of the tangles are? Could they be inside? So not being tangles exactly.
So, you can equally well ask if it can be extended to virtual knots. And one thing I could say is that I've asked that before you. It's one of the 19 questions. I don't know, you have to look for it. But I'm also asking, okay? But I should also say that somehow the atomic operations, so I defined a planar algebra, right? But really, the atomic operations, the most basic operations, are kind of different from what usually people do. So in quantum invariants, the basic operation is the concatenation of two strands. And it corresponds to multiplying in the quantum group or in the some universal enveloping algebra. And that's kind of the most atomic operation. Concatenating two strands, what I like to call stitching. Okay? But here, stuff happens on the faces, not on the strands. And the atomic operations are the phase merge, the gap touch, where you make two gaps touch and become a single phase, and the cordon operation, where, well, cordon is defined here, if it's a dictionary word, but the cordon operation means to cordon off a phase. So somehow the atomic operations are different. And so I'm actually not answering your question. I'm answering about virtual knots. I'm saying something about virtual knots. So what is a virtual knot? A virtual knot is basically crossings, concatenations, and you ignore planarity. And there might be a different type of virtual knots that's relevant here, where the basic things are crossings, and the operations are gap touch and cordon. So cordoning faces rather than connecting strands. And if I were to look for a generalization, I would first generalize the domain space, not the... That would be the first thing.
Thank you.
Any question from Zoom?
John. Haven't seen you in a long time.
Okay, let's give our speaker the floor.